Hey there, minions. Let's get back to work. Check this out. We're going to do the other indeterminate forms. This is when we had an exponential form. So 0 to the 0, why are these indeterminate? Because 0 to the 0, it looks like 0. Infinity to 0, these all have a reason. So like as the bottom, if we're just looking at the bottom as it goes, 0 like to some number is just 0. But if we're doing some number to the 0 power, it's 1. So which of these is winning out? If we do infinity to 0, infinity to the n is just infinity, but n to the 0 is 1. So is infinity beating 1 or is 1 beating infinity? Which one's taking over? And if we do 1 to infinity, it's not exactly 1. It's the limit as something approaches 1. So it means we're either coming in from the right of 1, having 1.000000001, but as that goes to infinity, the whole thing goes to infinity. And if we're coming in from the left side, 0.999999999 to the infinity, that eventually drops down to 0. Okay, so these are all conflicting things. Infinity or 0 here, infinity or 1 here, 0 or 1 here. These are all indeterminate, and so we are going to have a way of writing them using L'Hopital's. These all start with something in the form y equals f of x to the g of x power. What did we do before when we had an exponent in the variable? Y'all remember? We used logarithms to take it out of the exponent. So the example I'm going to do is using the infinity to the 0 case, but the other cases are similar. So like in this case, f of x is lining up with infinity, so I wrote a note that, and g of x is lining up with 0 the way I wrote it. So I start with y equals f of x to the g of x. I take the natural log of both sides. This allows me to bring g of x down. Now I can apply the limit. And just to show this is doing something in a L'Hopital form, we can split the limit into two different limits. And we said g of x is going to 0, so this is going to 0. And f of x is going to infinity, so natural log of f of x is going to infinity. We have 0 times infinity. We saw that was eventually led to a L'Hopital version. So what we can do is we can keep taking L'Hopital's rule until L'Hopital's rule doesn't apply. As soon as L'Hopital's rule doesn't apply, it means we actually got some sort of limit. So eventually we'll get to a point where this actually equals a limit. That's where we're going to start up there. So remember, this ugly thing was the same as the limit as x goes to a of natural log of y. So I'm just saying the limit as x goes to a of natural log of y equals the L. And now I can move the limit inside the natural log as we've been able to do before. It's been a while since you've done this, but limits are allowed to move inside stuff. And what we do here is to get rid of the natural log. We did this before when we did logarithmic stuff. We raise each side to be an exponent of e. E to the ln of x is just x, which means e to the ln of the limit as x goes to a of y just gives me the limit as x goes to a of y. The right side is e to the L, but the limit as x approaches a of y is what we started with. That was our natural log of f of x g of x. No, our y. Our y was f of x g of x. So y here is the same as f of x g of x, and now we have a limit for it. It's e to the L. Now this was a general form. We're going to look at specific cases where you can see it. The other scenarios do the same thing. Let's look at x going to the 1 over x power. As x goes to infinity, we get infinity as the base and 0 as the exponent. This is an indeterminate form. Don't forget, infinity to infinity is not indeterminate. 1 to the 0 is not indeterminate. Okay? Just get rid of those. There's other indeterminate forms that are not indeterminate forms that look similar to these. And they're back at the top. I'll show them again before we're done. So I'm going to say y equals x to the 1 over x. I'm going to take the natural log of both sides so that I can bring that 1 over x down. So I got natural log of y equals 1 over x times natural log of x. And we're going to do limit. And I rewrote 1 over x, ln of x. I just put this as one fraction, putting it on bottom. When we take the limit as x goes to infinity of that, we get infinity on top and bottom. This is an L'Hopital applicable opportunity. So we take the derivative of the top and bottom separately. The derivative of natural log of x is 1 over x. The derivative of x is 1. Now we've just got the limit as x goes to infinity of 1 over x is 1 over infinity. This just goes to 0. That's not our answer. 0 is not our answer because we were not working with the natural log of y. We wanted y. So what we're going to do is raise that. We're going to do the e thing. I'm going to move the limit inside the natural log. And then I'm going to raise both sides to be powers of e so that e to the ln cancel out. And I just got our limit equals e to the 0. So limit as x approaches infinity of y equals e to the 0, but y was x to the 1 over x. And that's what we wanted to find. So that equals 1. So it looks like the 0 exponent wins out here. Anything with a 0 exponent goes to 1. Let's take another look at another example. Why don't you go ahead and pause the video and try these? This is x to the tangent x. I did show that this is 0 over 0. Try to work out the following and keep going. I need a nap. All right, I will assume you did. I'm going to let y equal x to the tangent x so that I can take natural log of both sides, bring tangent x down. We're going to do the limit of both things. We get 0 times negative infinity. That is a L'Hopital applicable. I'm going to rewrite it by writing tangent x as 1 over cotangent x. And so now when I do the derivative, or second x goes to 0, I get negative infinity over infinity. You might want to just say this equals negative 1, but we don't know that. So don't make those assumptions. Okay? So what we're going to do is do a L'Hopital event. The derivative of natural log of x does get me 1 over x. The derivative of cotangent x is negative cosecant squared x. When we do this, notice I can just move the x to the bottom like that, and I can move cosecant squared to the top as sine. This is a little easier to read because I know those a little bit better. We end up with 0 over 0 again, which is different than infinity over infinity, but it's still an indeterminate form, which means we can L'Hopital again. If we L'Hopital again, we get negative 2 sine x cosine x on top. The bottom is just 1. Now when we stick in 0, this goes to 0. This goes to 1, so the 0 wins. 0 over 1 is just 0. That's not the answer. We didn't start with limit as x goes to 0 of natural log of y. So we got to get rid of the natural log. That's the hardest part to remember of these. So I've got the limit as x goes to 0 from the plus side of natural log of y equals 0. I can move the limit inside the natural log, raise each side to be powers or exponents of e. And now I just get limit as x goes to 0 of y. That's what we wanted. The limit as x goes to 0 of x to the tangent x. We see this equals 1 again. This equals 1. So the exponent won out over the denominator or the base being 0. That's not always the case. Sometimes the 0 wins. We can't always assume stuff is happening, okay? So that's how those work. You do natural log stuff. I wanted to show you how we can use this to see which functions grow faster. So let's take a look at x cubed, natural log of 3x, and e to the 3x. Which grows the fastest? Which grows the slowest? If we do limit as x goes to infinity and we do a fraction of it, we can see a comparison. So I did x cubed and natural log of 3x first. This is infinity over infinity, so I did L'Hopital's. We got infinity over 0 this time, which means the top is growing faster than the bottom. Okay? X cubed is growing faster than natural log of 3x. Then I'm going to compare x cubed to e to the 3x. Limit as x goes to infinity, x cubed over e to the 3x. They're both infinity. I can take L'Hopital. The derivative of the top is 3x squared. The bottom is 3 times e to the 3x. Again, infinity over infinity. Another L'Hopital scenario. We get 6x over 9 e to the 3x. Again, infinity over infinity. Take another L'Hopital. We get 6 over 27 e to the 3x. Now when we stick in infinity, we get 6 over infinity, which equals 0. Which means x cubed is not growing as fast, or it grows slower than e to the 3x. If I put them in order, it means x cubed was bigger than natural log of 3x, but slower than e to the 3x. If this showed x cubed was faster than both of these, I would need to do another comparison. But as it is, I can put them in order. Natural log of 3x is less than x cubed, which is less than e to the 3x. I will make a note of that here, though. If x cubed was faster than e to the 3x also, I wouldn't know how e to the 3x and natural log of 3x compared. So I would have had to do the same thing, another limit with them. Let's pop over to Desmos real quick, and I'll show you this in Desmos. Makes a little bit more sense. I wish I had this already set up, but we can do this real quick. I said, where's my natural log function? All right, now we're going to do y equals, we need e. Where's e at? Probably down in the same area. Exponent 3x. And now we're going to do y equals x cubed. I need an equal in there. So you'll notice as we go to the right, shit, it doesn't show up as a pin right here. My blue line is the exponent, the e to the 3x, and x cubed is that. For any particular value of x, like let's say we do it at 1 here. X cubed is only giving us, when we do it at 1, we're only getting a 1 here. But when I do e to the 3x, when I go up to a 1, we're all the way up here somewhere. So even at 1, e to the 3x is growing a lot faster. And we can see natural log of 3x grows the slowest. All right, that's it for this. Let me pop back up to the top, show you this again real quick. Oh, why can't I select you? There we go. It's not doing. I can't select it very well. Oh well. It might be easier to see the larger form right here using that. Write them down. Make sure you got them. And remember, these are bad. Ooh, that didn't do what I wanted it to do. These are bad. We can't use them, even though they look similar. So make sure you know which ones work. Okay? That's the end of this sequence. Peace. Get out there and do some damn homework, you lazy students. No, I know you're not lazy. You're all working hard. Good job. I'm proud of you guys.